Applications of calculus to the physical world. Cool title, hey? Spoke a little bit about displacement before. We in mathematics tend to use x as the pronumeral for displacement. I know there's this other horrible subject out there that likes to think they know how to do this, and they use an s. Where they get that from, I don't know. X makes sense, because we're dealing with straight line motion, and we just think of we're travelling along the x-axis. So it's logical to call it x. We just want to know where on the x-axis are we. Distance from a point, but with direction. With direction. And so that's now what the plus or minus means on the number. Because basically we're going to break everything down to straight line motion. Even when we eventually get to circular motion, that can be thought of as straight line motion. But that's to come. Okay? So really we only need to know, are we going forwards or are we going backwards? And we can define positive to be any direction we like. But if for now we just think of it as the normal x-axis or the number line, if you like, we'll imagine going this way to the, well, right as we're looking at it. That would be the positive direction, and going to the left, that'll be the negative direction. So velocity, symbolised V for velocity, that's a logical one. But also it's the rate of change of displacement with respect to time. So we could call it dx to t. Now when we're using calculus to talk about motion, there is another notation for the derivative. But it's simply one dot over the top. But we only ever usually use that notation when we're talking about motion, not when, derivatives in general. So it's the rate of change of displacements with respect to time. So it's speed, but with direction. So if I get a positive number, I know I'm travelling in the positive direction. If I have a negative number, then I know I'm travelling in the negative direction. Negative velocity does not mean I'm slowing down. Okay? You're still travelling with that speed, but just in the opposite direction. So that brings us to acceleration. A for acceleration, but it is the rate of change of velocity with respect to time. So we could call it dv to t, or we could call it the second derivative of displacement with respect to time. So using the dot notation, we could have x with two dots on top, representing second derivative, or v with one dot on top, representing first derivative. Now, it's the rate of change of velocity with respect to time. Now, whilst displacement has this partner distance, so we say displacement is distance with direction, velocity has its partner speed, so velocity is speed with direction. Acceleration has its partner acceleration. We sort of use the same word, don't know why we do, but that's life. So it's the rate of change of velocity with respect to time, but again, positive or negative. There's this term, I think I put it there, deceleration, which sometimes people use to talk about slowing down. There is no such thing as deceleration. It is not a physical thing. What it is accelerating in the opposite direction to which you're travelling. So if you imagine acceleration as pulling me or pushing me, well, if I'm travelling in the positive direction, but my acceleration's in the negative direction, so someone's going to be pulling me down, I'm going to slow down. So slowing down is still acceleration, but it's in the opposite direction to which you're travelling. So whenever the sign for velocity and acceleration is different, that's when we're slowing down. And that's what people think of as deceleration. Right? But there is no actual thing, deceleration. Okay, so we have those wonderful things. Here's a little diagram I'm sure you'll enjoy. To go from displacement to velocity, we differentiate. And then we differentiate. But to go back the other way, we integrate. Isn't that a lovely diagram? So here's a travel graph, but now, because I'm dealing with displacement rather than distance, we could have negatives on our travel graph. And this one, well, it might be a cubic, it might be a trig curve, don't really know, I haven't got the equation there, but we've got a curve with two turning points. And what I was saying before is a much useful piece of information is instantaneous velocity. I mean, when you're driving, for those that are driving, you look down at your speedo, it's telling you the instantaneous velocity because that is useful information. You want to know if you're going too fast or going too slow. If it was to read average velocity from when you started, I mean, it just wouldn't be a useful piece of information. It's not telling you how fast you're going. You want to know at that point. And we can do it just looking at the displacement time graph by looking at the slope at that particular point. Because the slope will tell us the rate of change of displacement with respect to time, which is velocity. So slope of the graph will give us instantaneous at that particular point, at that moment in time. Now, if I can draw the velocity time graph, let's assume that is a cubic. Well, if I differentiate a cubic, I should get... Yeah. So it'll turn out that my velocity time graph will be some sort of quadratic function. And how I can tell, well, look, up here we have a stationary point. So I know if I was to travel down, velocity would be 0 at that point. The slope here from 0 to 1, I'm increasing, so you'll notice velocity is positive. From 1 to 3, I'm decreasing, so you'll notice the velocity is negative. There is a turning point here. It corresponds to something on this graph. What do you think it corresponds to? Inflection. Yes, it's the inflection point. Okay. And the reason I know it's the inflection point is because of acceleration. And I'll come to that in a sec when we draw the acceleration graph. But again, I could find the instantaneous acceleration, similar to what I did with velocity with the displacement graph, because acceleration is the derivative of velocity. So the slope of the tangent on the velocity time graph would be the acceleration at that particular point. So here we go. Well, if I had a quadratic function for velocity, I should end up with... linear. Yeah, so there we go. We've got a straight line, a linear one. Now, going back to why I knew that was a turning point, because this was a point of inflection, if it's a point of inflection, then the second derivative would be 0. So I know the acceleration is 0. However, that means the first derivative of velocity is 0, so therefore it's a stationary point on the velocity graph. And so that's how you can tell where the turning points are, by looking at for the inflection points and the one above. Okay, so we want to find the distance travelled, not displacement, the distance travelled, then it would be 7 metres. We've gone up to 2, down to 3 and up to 4. Of course, another way I could have done it, if I knew the equation of this, because I integrate to go from velocity to displacement, I could find the integral. Now, in this case, distance would be like area. We'd have to break it up into above and below. Whereas displacement would just be the straight integral. Okay. Or I could just look at my displacement graph and it looks like we've gone backwards a metre, so -1. We ended up going 1 metre in the negative direction. Average speed. So average speed, total distance that I've travelled, because distance goes with speed, over time taken, where we used 4 seconds for this one. So average speed is 7/4. Average velocity will be displacement over time, so that's -1/4. Okay, so here's one where they haven't given us the graph. So yes, we worked with all these travel graphs. We don't actually need the graph. If we've got the equation, that should be good enough to work out all the information from what we know about calculus and locating stationary points and things like that. So our displacement, our little particles travelling according to this, a cubic, t cubed minus 21t squared, travelling along the x-axis. Find the acceleration. So what's the formula for acceleration? So really it's just saying differentiate twice. And there we go. So velocity 3t squared minus 42t, acceleration 6t minus 42. When is it stationary? So now you can think about it in all sorts of different ways. It's lovely, the word stationary. Stationary, I could think of it as velocity equals 0, I'm stationary. Or I can think stationary points. First derivative equals 0, which again is velocity. It all ties in nicely. So we want to know when velocity is 0, solving that little quadratic. So initially it's stationary, and then again at 14, which brings up an interesting point. If I'm starting and I'm stationary, well, why do I move? Right, that comes from the acceleration. Acceleration, or what we tend to be interested in, although we don't use this terminology till we get to extension 2, force. Force is mass times acceleration. If I'm standing still but someone applies a force to me or gives me an acceleration, I must move. So it is possible to be stationary initially. So we are stationary initially, and again after 14 seconds. So this particular particle, again we're going along our x-axis, starts from rest, t equals 0, but we're not going to start at the origin this time, we're going to start at x equals 7. They've given us an acceleration formula. We want to find the position of the particle at t equals 3. Okay, this is doing it as an indefinite integral. So we get plus a constant. Sub in the conditions that we know between time and velocity to work out the constant. Turns out to be 0. So there's velocity. What do we have to find? We still want the displacement formula. So we'll integrate again. Some link between time and displacement. So we know when t equals 0, x equals 7. Sub in, get our constant. We now have our formula for displacement, and so we can now substitute in and find its position. So the position is at 43. There you go. So however you want to write it, it's at x equals 43, or if you want to be fancy, you can say, well, I know it's 43 units to the right of the origin, or something like that. Now, if I did it as a definite integral, dv to t, acceleration, is 2 plus 6t. I separate the variables. So dv's on one side, the t's on the other, the integral, and I match up the conditions for the integral. I know when t is 0, so over here times 0, but velocity is also 0 at that point as well. And I'm trying to find a link between t and v. And so I just do these two integrals. And we get it without actually having to find the constant. We come up with 2t plus 3t squared. But now I want to work out the answer for displacement. So doing it this way, I don't actually need to work out the formula for displacement. Because what I now say is, well, velocity is dx to t. Again, separate the variables. But all I'm now going to say is, well, when t equals 0, displacement is 7. I want to know what x is when t is 3. And do a straight. So, yes, I sort of get the displacement formula, but I haven't had to worry about finding the constant, because I just sub in as a definite integral, and I'll end up with, well, x minus 7 is 3 squared plus 3 cubed. Move the 7 to the other side, which in effect was the constant, was x equals 43. I tend to prefer that second way myself. I think it's a neater, cleaner solution, but also I think it's a quicker solution. HSC question. Particles moving in a straight line. Wow, this one's really interesting. X equals t minus 2 on t plus 2. So it's some sort of hyperbolic function. T is measured in seconds. What's the displacement when t equals 0? So in other words, where is it initially? So sub in 0, oh okay, -1, we're 1 unit to the left of the origin initially. Show that, oh it's a 2-unit question, okay, there's a bit of a gift. Show that x equals 1 minus 4 on t plus 2, hence find expressions for velocity and acceleration. So alright, oh what do you know, 1 minus 4 on t plus 2, if I do an algebraic fraction, oh, t minus 2 on t plus 2. Alright, so we've got x. I guess what they're doing is giving a huge hint that, hey, this is going to be easier to differentiate than t minus 2 on t plus 2. So let's find velocity, differentiate, minus the derivative on the function squared. I get 4 on t plus 2 squared. Differentiate again to get acceleration, minus the derivative on the function squared, and we get minus 8 on t plus 2 cubed. Is the particle ever at rest? Give reasons for your answer. Okay, there's our velocity function. Is it ever at rest? Why not? So give reasons for your answer. Yeah, it would be impossible for that function to equal 0. We've got a constant on the top of the fraction. Can't equal 0. So we know that can't equal 0. So the particle is never at rest. Oh, that's probably not a great reason. All I've said is no, it's never 0. Maybe I should explain it a bit more, saying, well, when you got a constant on the top or something like that. But what is the limiting velocity then? So this particle is never going to stop. That's what we're basically saying. It's just travelling along. Come on, when are we going to... Are we there yet? Are we there yet? And it never gets there, poor little thing. Little particle travelling. How fast or slow does it end up going? So in other words, what we're saying is, as time approaches infinity, what's the limit of velocity? And velocity, remember, was 4 on t plus 2 all squared. So as t approaches infinity, what does that approach? Yeah, it does. Approaches 0.
So it will say, oh, I'm giving up.
So, if it was possible to reach infinity, it would eventually stop. So it's getting slower and slower and slower and slower, but never ever actually stops. Of course, you could think of the graph. There's the graph, 4 on t plus, and you can see it goes asymptotic to the axis there. So the limit's approaching 0. Let's try another one. Particle straight line, seconds. This time it's a trig function that's travelling along. Sketch the graph. So in other words, let's find all the information. The amplitude is 1. I've shifted it up 3. The period is pi. I'm going to mark off my divisions, every pi on 4. So here we are. Now, a sine curve normally starts at the origin, but we've shifted it up 3. So I'm going to start at 3, and then we go up and down, up and down, up and down. Whee! There we go. So there's our displacement graph. Using your graph, or otherwise, find when the particle is at rest. Well, it's a lot easier to look at the graph because we know it's when velocity equals 0, stationary points. So we want to know when is it equal to 0, and so we can just look at the graph and go, oh, well, there's one there at t equals pi on 4, and at that point x is 4, and then there's one there at 3 pi on 4 and 5 pi on 4 and so on. So yeah, a lot easier than actually doing the calculus. Just look at the graph. Describe the motion completely. This is where you can have fun. Oh, well, what did I say? Did I use big words? Oh, my word, I did. Oscillates. The particle oscillates between 2 and 4. That just means travel backwards and forwards, of course, with a period of pi seconds. What a life that particle has, eh? It's on the number line, it's at 2, it goes, let's go and investigate. 3, ooh, this is nice. 4, better not go any further, might go back. Okay, 3, 2, oh no, I'll just stop there. Okay, this way, 3, 4, can't go any further. It just does that, forever. Interesting life. Okay.